Hi, Dr. Revis here. In this video, I will show some example calculations of gas laws. Specifically, this video will consider Boyle's law, Charles's law, Gay-Lussac's law, combined gas law, ideal gas law, and we will take a look at working gas law problems at STP, standard temperature and pressure. We show you here some equations for the gas laws. We have Boyle's, Charles, Gay-Lussac's, Avogadro combined gas law. These 5 gas laws are comparative. In other words, you'll always have a starting condition and a final condition. You'll have one set of conditions versus a second set of conditions. So, Boyle's, Charles, Gay-Lussac's, Avogadro combined will always be comparative. That's one way to know you're using one of these laws. Then we have the ideal gas law. PV equals nRT. We also have an example here of a modification of the ideal gas law, which allows you to calculate mass or molar mass. Then we have density formulas here for relating them to ideal gas laws. And we also have a molar mass when we have density. We're also noting this one, standard conditions. Temperature is 0 C, but we always report temperature in Kelvin, K. Then standard pressure is 1 atmosphere or 760 millimeters of mercury. And an STP is important to note that 1 mole equals 22.4 liters. We have a conversion of 1 atmosphere to 760 millimeters of mercury or 760 torr. Note that when we use the ideal gas law equation, there are universal gas constants, and we have to match those to the units. That is an important thing to remember, that matching the R universal gas constant to the rest of the units in the problem is very important. So let's get going by working a problem. Here's the problem. An inflated helium balloon with a volume of 0.55 liters at sea level, and sea level is 1 atmosphere, is allowed to rise to a height of 6.5 kilometers, where the pressure is about 0.4 atmosphere. Assuming that the temperature remains constant, what is the final volume of the balloon? A helpful thing to do when you have a problem like this is to mark off all your variables right in the problem. And so we show you that here, where we marked off the pressures and the volumes. And notice in this case, we only have pressure and volume. When the problem involves only pressure and volume, that's a Boyle's law problem. Boyle's law assumes that temperature remains constant. Therefore, we're only working with pressure and volume. And so we're comparing P1V1 to P2 V2. Okay? So here we simply take Boyle's law equation, we rearrange it to solve for V2, and we put in the variables. We've shown you the initial conditions and the final conditions. We put in each of the variables. We check to be sure the units match, and since the units match, we work the math through and we get 1.4 liters. Let's work another problem. A container with a flexible wall holds a gas that is cool from 65 degrees C to 22 degrees C with no change in pressure. If the container volume was 4.5 liters initially, what is the volume after being cool? We take this problem and we mark up all the variables, and we note in this we have volume and temperature, which means it's a Charles's law. One of the other important things to do when you have temperature is to automatically convert it to Kelvin. That is a common mistake made with these problems, that students often forget to convert it to Kelvin. So as soon as you see temperature, convert it to Kelvin. So since this is Charles' law, and because we only see in this problem V and T, if we use the variables in the problem, it will tell us which law is involved. So this problem only has V and T, therefore it's Charles's law. I set up the ratio for Charles's law. I rearranged this equation to solve for V2. And when I put in my values, I get 3.9 liters. I obtain this value by starting with initial conditions, final conditions, and then calculate it to the proper number of significant figures. Let's work another problem. Argon is an inert gas used for light bulbs to retard the vaporization of the tungsten filament. A certain light bulb contains argon at 1.2 atmosphere and 18 degrees C and is heated to 85 degrees C at constant volume. Calculate the final pressure. Again, I mark up my problem with all the variables. I see that I have pressure and temperature involved here. As soon as I see its pressure and temperature, I know this is a Gay-Lussac's law. So I set up my relationship of P1 over T1 equals P2 over T2 for Gay-Lussac's law. I also automatically convert my temperatures to Kelvin so that I don't make that mistake. So I observe my initial conditions and my final conditions. I rearrange the equation to solve for P2. I put in each of the units and I obtain 1.48 atmospheres for this particular problem. Again, this is an example of Gay-Lussac's law because Gay-Lussac's law involves pressure and temperature. What about the next problem? A winter balloon with a volume of 44 liters is filled with 2.0 moles of helium. What is the final volume in liters if 3.0 moles of helium are added to give a total of 5.0 mole of helium if the pressure and temperature do not change? Since pressure and temperature do not change, and I note in this problem I only have volume and moles, therefore this is an Avogadro's law problem where I set up the relationship of V1 over N1 equals V2 over N2, since this law is comparative. Now, notice something here. It's very important when we start to assign the variables. The initial conditions are 44 liters and 2 moles. There was an increase by 3 moles to 5 moles. Do not make the mistake of using the 3 moles, which is the value of the increase for the final. What you're interested in is how many moles there were initially and how many moles there are finally. Do not consider the intermediate values. Okay? So with that, we rearrange the equation to solve for V2. We put in all of our values and we obtain 110 liters with 2 sig figs, which matches the initial 2 sig figs in our problem. Let's consider the next problem. A small bubble rises from the bottom of a lake where the temperature and pressure are 8 degrees C and 6.4 atmosphere to the water surface where the temperature is 8 degrees C and the pressure is 1.0 atmosphere. Calculate the final volume in mils of the bubble if its initial volume was 2.1 mils. We mark up our problem and we observe we have P, T, and V involved in this. When we see P, T, and V involved, we recognize this to be a combined gas law equation. So we set up our P1, V1 over T1 equals P2, V2 over T2. We record our initial conditions and our final conditions. Note that we must change temperature from C to K, degrees C to K. We rearrange the combined gas law equation to solve for V2. We put in all the values and we obtain 14 mils for this problem. Again, we know that this is a combined gas law by simply marking up the variables in our problem. The next problem. Sulfur hexafluoride is a colorless and odorless gas. Calculate the pressure in atmospheres exerted by 1.82 moles of the gas in a steel vessel of a volume of 5.43 liters at 69.5 degrees C. We mark up our problem with the variables involved here. We change our temperature right away to K so that we don't lose sight of it. And what we observe is that we have variables involving P, V, T, and N. We right away recognize that this is an ideal gas law equation because we have PV equals nRT. Note that R is a constant, a universal gas constant. Therefore, we take this equation and we set it up to solve for pressure. We take the equation, we put in all the values, we use the proper universal gas constant R for this problem, and when we calculate the values, we obtain 9.42 atmospheres. Again, we recognize this as an ideal gas law equation or ideal gas law problem because when we marked up our problem, we had P, V, T, and N. When we see that in the problem, we right away know that this is an ideal gas law problem. Occasionally, calculations for gas laws will be carried out at what's called STP, Standard Temperature and Pressure. Standard temperature is 273 K or 0 C. Pressure is 1 atmosphere or 760 millimeters of mercury. Here's our problem. Calculate the volume in liters occupied by 7.40 gram of ammonia at STP. As soon as we see STP, we know that's 273 K. We know that it's 1 atmosphere. And note that we have grams instead of moles, but that's okay. We know that if we have grams, we can get to moles. If we have moles, we can get to grams. Therefore, we will use dimensional analysis. So we will use unit analysis to carry out an STP problem. So here's the strategy. 1 mole of an ideal gas occupies 22.41 liters at STP. So we would note that, and we will use the molar mass of ammonia to get to moles of ammonia. So we set up our given at 7.40 gram ammonia. We carry this through a standard unit analysis with grams of ammonia on the bottom and 1 mole of ammonia on the top. And we then convert it using standard volumes of 1 mole, which 1 mole is 22.41 liters, and we obtain 9.74 liters. So there we have it. That's the volume. An alternative way to do this would be to solve for the moles first and then determine the liters. And this is perfectly permissible. So we would take 7.4 grams and we would convert this to moles using unit analysis as shown here to 17.03 grams on the bottom and 1 mole on the top. And that gives us 0.435 moles of ammonia. We would then take the moles of ammonia and we would convert it to liters using the standard 22.41 liters. So essentially, method B divides method A into 2 steps, but it is otherwise exactly the same. Still, there's one other approach that's worth noting to solving this problem. Take a look at it on this slide. In this case, we're going to take a look at STP conditions and we're going to solve the problem using dimension analysis and a gas law equation. Specifically, we're going to use an ideal gas law equation. So the strategy is, since it's STP, we could convert the grams to moles, then use the ideal gas law equation to solve for volume, since we know T equals 273 K and P equals 1 atmosphere at STP. So we solve for moles as we've done on the previous slide. We would then take the ideal gas law equation and rearrange it to solve for volume. In this case, V would equal nRT divided by P. We take our standard R times the number of moles that we've calculated times K, temperature, divided by 1 atmosphere, and we obtain 9.74 liters as we did in the previous calculation. So again, in this case, we calculate the moles, and then we take those moles and plug it into the ideal gas law equation, and we obtain the number of liters. So there you have it. Example calculation of gas laws. Calculation for Boyle's, Charles, Gay-Lussac's, combined, ideal, and STP.